look at wave equation using finite difference scheme. So wave equation is this, we did in spectral method. Okay. Now let's do again discretize it like that in space. Okay. So that will give us so d phi. So I skip that step. D phi I equal to minus c first derivative in x. Okay. So I'm using central difference again. So this is d phi by dt at I. Okay. And that is given here. Okay. Now, central difference scheme, phi I plus 1 minus phi minus 1 by 2h. Now, stability, if you, okay, number one, stability. Let's see how that is. If you substitute, again, I take a Fourier mode and see whether the f is increasing in time. Okay, by the way, here is the wave equation, so f is flat. F is, in fact, should not explode. So if you substitute it here for equation for f, I get this. I just substitute it here. And this equation, unfortunately, is telling us that f is increasing in time, right? Modulus of this is greater than 1. Okay, so it's unconditionally unstable. It's unstable. Bad news. So central difference scheme is unconditionally unstable. Okay, so this will keep growing in time. So there's something called Upwind scheme. So since wave is going forward like that, it's going forward. So we use the derivative, you know, we have to compute d phi by dx at I. So we use phi I minus phi I minus 1. So I want to compute this, so I minus 1. So I just take the derivative, divide by h. Okay. And this scheme is stable. It turns out that you can show it for given some delta t, substitute it e to power ikx ft in this equation, and we get this equation for f. Okay. Now, is bit of algebra involved here. We can look at in the book, and you find that this is less than 1, the factor of when this condition is there, 1 minus alpha cos h, 1 minus cos h, cos kh, and kh is, cos kh is, worst case is minus 1. Because we had, I had shown you the curve, kh is pi. So when kh is pi, then cos kh is minus 1. So this becomes 2. Okay. So the worst scenario, so basically this always remains positive. Cos kh is always less than 1. Okay. So this part is always positive. So 1 minus alpha is greater than 0. So alpha is less than 1. And alpha, I have written it here. Alpha is c delta t by h. I forgot to say that's critical. So alpha must be, for this condition is, alpha must be less than 1. If you want this whole thing to be greater than 0. So that gives us the condition that c delta t by h is less than 1. Okay. So delta t is less than h by c. And this is also called CFL condition. Okay. The same CFL condition we discussed before. Okay. Now, so let's compute them by both the methods, upwind as well as center difference. Upwind is stable. Please remember, if you use delta t less than c by h by c, then it's stable. Okay. So the center difference scheme, this is t equal to 0, t equal to 1, t equal to 2. So the wave is going to the right, but you can see that is unstable. You know, so we are generating more Fourier modes. Okay. The shape of the wave is getting destroyed. Okay. So central difference scheme has a problem, it's unstable, so it's generating more modes. And wave is losing shape. Okay, not good. What about upwind scheme? Upwind scheme, this is t equal to 0, t equal to 1, t equal to 2. So shape of the wave is same, but is spreading. Okay, so this is diffusing. So you can see that from the expansion of the term, which term we are missing out. So we use 5i minus 5i minus 1. So it turns out we can easily show that this is generating higher order term, d5 and dx. This term is getting generated. Now this term, which I didn't do in this class, but this term is the diffusion term. If you do the Fourier transform, there's ik cube phi k, Fourier transform, okay? This one. So this term does not damp the solution, but it diffuses the solution, okay? So, of course, so central difference fixing is diffusing, okay? So it is diffusive, so it is kind of spreading things out, and this is dissipative. So what it does, it introduces the term d square 5 and dx squared. Okay, both these terms do not exist here in the system. We have equation d5 by dx. Okay, c d5 by dx minus c d5 by dx. But these are the terms which are generated because of the scheme adopted. So here I get the amplitude to be decreasing. Here amplitude is not decreasing much, somewhat. Okay, but it's diffusing. It's just getting spread out. Okay, so both of them have trouble. Okay, so spectral is accurate. You see, spectral is giving you a good solution. In fact, it will just keep moving. So spectral is a good method for idealized boundary condition. Okay, it's perfect in fact. So there are limited. Wave equation has a problem with finite difference scheme and problems of this sort. Diffusion equation was okay. It was behaving okay, but especially the wave equation, it should be keeping shape and moving to the right for C positive, but we are getting this both dissipation for upwind scheme and diffusion for central difference scheme. Okay. Now Burger's equation we can solve now. Once we know how to solve diffusion and wave, then we can use it to solve Burger's equation. So this is Burger's equation, and I'm using this is upwind scheme. Okay. So when U is positive, this is not really the wave equation. No? So we can write this C dx by d. Okay. C is constant for wave equation, but here I got U, which U is variable in X. Okay. So the idea is that let's look at sign of U. If U is positive, then use upwind with forward upwind, and if U is negative, then use backward upwind. Okay. So you can see that here is this is what I had written in the earlier slide: ui n minus ui minus 1n. Okay. So interpretation is that the signal at I is affected by I minus 1 if the wave is moving to the right. I mean, the wave is moving to the right. So the guy in front will be affected by guy at the back, okay, when it's moving to the right. But when it's moving to the left, then I minus 1 will be affected by I moving to the left. So I have, or I is affected by I plus 1. I is affected by I plus 1. Okay, so like that. So we use I plus 1 minus I. Okay, ui plus 1 minus ui. So this part is this upwind. Okay. Now this double derivative is computed by standard central difference scheme. Okay. Upwind we want to be a bit careful, but often we can use RK2 or RK4, and is accurate. There always error, but is controlled error. Okay. So this is by I think RK2 method, and we are getting roughly similar structure as spectral. Okay. There's a bit more error in this, but we are basically getting that. So this is RK2. I mean, I'm using small delta t, and my grid size is slightly bigger instead of 64, and we're satisfied. Okay, that's why I think nonlinear problems we can't be sure if the error is getting somewhat cancelled, or things are getting stabilized, things are getting, yeah, yeah, it's just by trial and errors often. Okay.